So I'm going to talk about sustainability for offset-based response time analysis. Me, myself, is Jukka Mäki-Turja, and I've conducted this research with Hänninen and Mikael Sjödin at Mälardalens University. So first I'm going to talk about a little bit what sustainability is and why it's important. And then introduce the offset-based or transactional task model for response time analysis. And in that, introducing the demand bound function. And in sustainability for offset-based response time analysis, we define two concepts, subsumed points and subsumes demand bound functions, which is basically the core contribution of this paper. Back. And then I'm going to do an engineering example. And I can say that there are two main uses of offset-based response time analysis. Either it's for distributed systems and doing a holistic scheduling, or hybrid static and dynamic scheduling, which we have been working on together with a company here in Sweden that adopts this and has actually implemented a lot of stuff in this regard in their products. What is a sustainable scalability test then? You can say that a sustainability test is when its parameters behave better than a specification, then this yields that the system still remains schedulable. For example, worst case execution time. As long as the execution time is lower than the worst case, then you can say that the schedulability test still holds valid. So typical sustainable parameters for most schedulability tests are worst case execution time, as I mentioned, or even period or minimum interarrival time. And in that case, if period is longer or minimum interarrival time is longer, then the schedulability test is still valid, thus sustainable. This looks a little strange, but never mind. In the traditional response time analysis, it was assumed that worst case workload occurs when all tasks are released simultaneously. However, when we have offsets, here we have a task executing for one time unit, or is it two, with an offset of 0. And then at offset of 4, we have task that executes 4 time units. And they are grouped into this called transaction, and this transaction have a period of 12. And the traditional assumption is that all tasks are released simultaneously, but here it is not possible. Here it becomes that at least one task out of every transaction, we call this a transaction, coincides with the critical instant. So either this task coincides with the critical instant, or this task coincides with the critical instant. And from that, we go into talking about offsets in general, and they are not sustainable. There are no way of saying that if offsets change this way, it's for the better. So and Burns and Barua state that it's best to ignore such parameters, that is, assume that they are zero at the cost of some precision in the response time analysis. And there are two most common uses of response time analysis with offsets, either the holistic schedulability test in distributed systems, or what we've been working more on is hybrid static and dynamic scheduling, where you basically make the static schedule as a transaction, because the offset are nothing more than time separation between tasks. And from this, we see that we have an execution demand of this transaction. If, let's assume that this task is the one that coincides with the critical instant, then we see that we have 2 units of execution. Oops. Then we have 2 units of gap. And then we see that we have 4 units of execution and then a gap. And that's the period, and it repeats itself. However, it's much as likely that this 4 chunk coincides with the critical instant. Then we have 4 units of execution, and then we have some gap in between, and then this one task comes in, and this is the execution demand that they require. And in the approximate analysis, what we do is we basically overlay them over each other to get the maximum interference for this transaction. So here we have interlaid these two in this C figure, and then basically taking the maximum to get the demand function for this transaction. Feel free to ask any questions if you're uncertain. And with
it's okay, half times, kind of.
Okay. We defined in an earlier paper subsumed points. Is basically if we have a point here, PA, then everything in the gray area all points in the gray area are subsumed by this point. Those white points are not subsumed. It's basically saying that it has to lie under this line. That's the first part. And it has to lie to the right of this slant. And this is going to help us to get to the definition of the subsumed demand bound function. It basically says that the bound function A subsumes the bound function B if and only if there is a PB in the convex corners of DBF, then there is a convex corner of the BFA, so that PA subsumes PB. So basically saying that if, let's say that this is PB, then this point must be subsumed by some convex corner of PA. And this one must do the same. And this one must do the same. And basically this is the main scientific contribution of the paper. As an example transaction, we're gonna have 3 tasks, T1, T2, T3, with execution times of 3, 2, 1, offsets 0, 5, and 10. And we ignore jitter for simplicity. So you can see here that the blue line corresponds to task get coinciding with the critical instant. Executing for 3 units, going 4 units until task 2 comes in. And then we have to do the same with task 2. It's the brown line here. And the same with the task 3. And then we have to take the maximum to get the demand bound function for this transaction. From our example, we have generated all the possible unique offsets. By unique, we mean that it's the relation between the offsets that are of interest. So for example, we have 0, 5, 10 here. You can say 1, 6, 11. And that is not a unique transaction. It's just shifting everything one step. So we collect only the unique transactions.
So 5, 0, 10 wouldn't be unique, right?
What?
5, 0, 10 would not be unique, right?
5. Let
A
me
permutation.
see.
Permutations are not kind of allowed.
Depends on the execution time.
Yeah.
If they're same execution time, then permutation is also same. But here we
Right.
have different execution time that complicates matters.
Mhm.
So we generated all possible offsets that are sustainable and got this list. And from this list, we can further merge to get a more compact representation of this information. For example, the first row cannot be merged with anything. But if you look at row 2 to 7, you have 0, 6, 10, 0, 6, 11, which means that those two rows can be merged so that you have 0, 6, and 10 to 11. And up to 12. So, and depending on what you're interested, what task here you're interested in, you can merge and generate these cases so that different tasks are highlighted. So for example, here we see that 0, 5, 10 is our original transaction, and then 0 and task 2 can have an offset between 6 and 7, while offset 3 can have between 10 and 12.
Mhm. Maybe I can ask a question. I was looking into original reviews from the reviewers, and it seems that one of the reviewer was concerned about the complexity of your approach. So
yes,
what would be the complexity of a sustainability test?
If you want to do this robustness analysis, you have to generate all possible offsets, and that is exponential.
Exponential, right? Okay.
Yeah. However, another use is that in this static hybrid static and dynamic scheduling framework, you can work with doing a static schedule, make it a transaction, and do some elaboration on it.
Right. That would be kind of two
and
parts.
then you don't necessarily need to do a rescheduling, and you don't generate all the possible offsets, but you do the changes, and then you can look, okay, the demand function is lower than the original, then I don't have to do any rescheduling test.
Mm-hmm. So did you try to estimate the complexity of this part, like just partial checking? Would it be, this should be lower than exponential? Maybe it will be polynomial, or
what polynomial you
the complexity of the incremental part of checking should be lower than exponential, but do you have some guess? I mean, what would it be like?
No, I don't have. We didn't.
I think a lot of people are interested in this question because it's kind of gives you a feasibility of your approach. You know, is it a kind of applicable or not? And so maybe in your future work, I think this one of important points made by the binary reviewer, and you should consider it, I think.
Yeah.
Another question is about a tool you mentioned in the end of your paper. You're currently implementing a commercial tool, and so can you say a little bit about it? What programming language, for example, you use? What is the input to this tool? What is the output, etc.?
It's they have a tool suite to generate control systems for heavy machinery, and they have a component-based framework where they generate an execution environment, an operating system, basically, where you have hybrid scheduling, where you have interrupts on one level, then you have the static schedule, and then you have lower priority dynamic tasks.
Mm-hmm. This would be done in C, C++ languages? Or
yeah, C++.
Right. So the input is kind of real measurements, execution time, that would be the input to the tool, yes?
Yeah.
Mm-hmm.